Calculus and analysis.
Single variable calculus, the study and analysis of functions of a single independent variable and single dependent variable. It studies ideas of change in motion and the accumulation of quantities. This includes concepts of the limit, the derivative, and the integral, which adds up an infinite number of infinitesimal quantities and is used in part to compute the cumulative effect of infinitesimal changes. It also includes the convergence and divergence of infinite sequences and infinite sums, as well as Taylor series. Applications of single variable calculus include modeling physical motion, optimization, supply and demand, mechanics, dynamics, and statics in engineering, differential equations, heat transfer, computer graphics, digital signal processing, and more. Multivariable calculus, the study and analysis of functions with multiple independent variables or multiple dependent variables. This extends the same concepts from single variable calculus, including limits, derivatives, and integrals to multiple dimensions. Applications include higher dimensional versions of all the applications of single variable calculus, but also include the geometry of curves and surfaces, arc length, surface area, volume, fluid dynamics, multivariate optimization, partial differential equations, computer animation, and more. Hey, I once failed a calculus exam because I was seated between two identical twins. It was really hard to differentiate between them. And if you like that joke, hit that subscribe button. And if you didn't, hit the subscribe button anyway, because we want you to be part of the Scholar Sauce community. All right, let's get back to the video. Real analysis. This is the abstract study of concepts in calculus and includes rigorously analyzing real numbers, infinite sequences and series of real numbers, and real valued functions. This includes understanding rigorously convergence, limits, continuity, smoothness, differentiability, and integrability. Complex analysis. This is the study of the calculus of complex valued functions. This extends the basic ideas of single variable and multivariable calculus to functions on the complex plane. This includes extending the study of differentiable functions to holomorphic functions. It also provides a description of logarithms, exponential functions, and trigonometric and hyperbolic functions in a unified way. Complex analysis has applications to electrical engineering, quantum mechanics, signal processing, and control theory, as well as applications to other fields of mathematics including algebraic geometry, number theory, and topology. Measure theory. This topic generalizes the notions of measuring the size of sets, including geometrical, physical, or probabilistic sizes. These measures can be used to generalize integration using the Lebesgue integral. Measures also have applications to probability theory, integration, functional analysis, quantum physics, and more. Functional analysis. This is the study of the infinite dimensional vector spaces of functions, typically with a norm or inner product that induces a topology on the space. As such, this is an extension of both real analysis and linear algebra. This also provides a strong framework for solving differential and integral equations. Applications of functional analysis include numerical analysis, signal processing, financial mathematics, stochastic calculus, and quantum mechanics. Numerical analysis. This is the study of numerical methods of approximately solving differential and integral equations, as well as other problems containing continuous variables. It also includes the development and study of algorithms that solve such equations to understand their stability and convergence. Applications of numerical analysis include any branch of the natural, physical, or social sciences, computer science, engineering, medicine, or business where exact solutions of problems with continuous variables cannot be computed. In particular, this allows us to bring to bear the immense computational power of computers to solve problems when exact methods are not available or applicable. Non-standard analysis. This is a reformulation of single and multivariable calculus by building on a rigorous definition of infinitesimal numbers. It includes the use of the hyperreal line and replaces the need of epsilon delta approaches to calculus concepts. This provides a rigorous version of the more intuitive ideas that were the driving force behind Gottfried Wilhelm Leibniz's development of calculus. Applications of non-standard analysis are the same as those for calculus, but it is used less often as it is not the traditional way that calculus is taught. However, proponents of this treatment of calculus argue that this approach is far more intuitive for students and helps them understand calculus concepts far better than the traditional approach. Ordinary differential equations. Differential equations are equations involving the derivatives or instantaneous rates of changes of functions. The topic of ordinary differential equations, or ODEs, focuses on the study of equations that involve the derivatives of functions with only a single independent variable. This includes finding solutions to such equations, proving the existence and uniqueness of such solutions, as well as studying the behavior of solutions and how they change with varying initial conditions. ODEs include important equations in science such as Newton's second law of motion, exponential growth and decay, Newton's law of cooling, the dependence of pressure with altitude, motion of a particle with or without drag, Hooke's law of simple harmonic motion, motion of a pendulum, the rate of chemical reactions, and more. Partial differential equations. Partial differential equations, or PDEs, are differential equations that involve partial derivatives of functions that have more than one independent variable. Like ordinary differential equations, the study of this topic includes finding solutions to PDEs, proving existence and uniqueness of solutions, and studying the behavior of such solutions and how they change with varying initial conditions. A wider class of equations in science and engineering are partial differential equations. These include the wave equation, the heat equation, Maxwell's equations for electromagnetism, the Navier-Stokes equations for fluid dynamics, Schrödinger's equations in quantum mechanics, the Einstein field equations in general relativity, and so much more. Dynamical systems. This is the study of systems where a function describes how points in a space move with time. Such systems can be described using ordinary differential equations. Using numerical analysis and ergodic theory, this provides a framework to model such systems with time and space measured in a discretized way. Dynamical systems occur in physics, biology, chemistry, engineering, economics, medicine, and even history. Some dynamical systems may be chaotic, and hence this topic includes chaos theory. Dynamical systems are one of the primary ways that calculus is applied to real life. Chaos theory. This is the study of a class of differential equations that are highly sensitive to initial conditions. This means that the solutions change dramatically with just slight alterations to the initial conditions. Differential systems that exhibit chaotic behavior are deterministic, meaning that their initial conditions determine unique solutions, but this sensitivity to initial conditions gives the solutions of the system the appearance of randomness. Chaos theory deals with analyzing the behavior of such systems and how to model chaotic systems. An important challenge of modeling real-life chaotic systems is that all measurements we can make are ultimately approximations of reality, which means that any initial conditions we put into a model will necessarily be different than the actual values of the initial conditions. The chaotic behavior of the system implies that any long-term prediction from the model will be very far off quicker than one would typically expect from modeling differential equations. Chaotic systems abound in nature, including in fluid flow, heartbeat irregularities, and weather. This is one of the main reasons that it is difficult to accurately predict weather out past a few days.
Algebra.
Elementary algebra. Elementary algebra is the type of algebra that one might learn in high school and the first year of college. It is the study of the arithmetic of real numbers and some elementary functions of a single independent variable. This includes how to manipulate algebraic expressions that include unknown quantities, as well as solving equations and inequalities for those unknown quantities. This also includes the introductory study of single variable real-valued functions, such as polynomial, rational, radical, exponential, and logarithmic functions. This may also include a basic introduction to linear systems of equations. Abstract algebra. Abstract algebra is the study of algebraic structure. It includes studying algebraic systems where abstract operations are applied to a set of elements. These operations are assumed to follow a set of rules called axioms. Such systems are then studied abstractly, meaning that the operations and elements are not concretely defined, but left general so that the results might be applied to any concrete system where the behavior is observed. A variety of algebraic systems are well understood. These include, but are not limited to, the following. Groups. These are sets that have one operation defined on them that satisfies the group axioms. If the operation is commutative, then the group is called abelian after Niels Henrik Abel. Some examples of groups are the integers with addition, the non-zero real numbers with multiplication, permutations of a set with the operation of doing the permutations in succession, and the moves on a Rubik's Cube with the operation of doing the moves in succession. Rings. These are sets that have two operations defined on them that satisfy the ring axioms, one referred to as addition, the other as multiplication, though they do not have to be the operations with those names defined on the real numbers. If the multiplication operation is commutative, has an identity, and every non-zero element has an inverse, then the ring is called a field. The integers with addition and multiplication are a ring. The rational, real, and complex numbers with addition and multiplication each are fields. Square matrices with addition and matrix multiplication are a ring. The integers modulo n for some positive integer n are important rings that play a role in cryptography. Vector spaces. These are sets of objects referred to as vectors that form a group under an addition operation, but are also associated with a field of scalars and have a scalar multiplication defined that indicates how to multiply a scalar and a vector to obtain another vector. Geometric arrows in n-dimensional Euclidean space, column or rows of numbers, matrices, and polynomials of degree at most n are all important examples of vector spaces. Many data structures are another important example of vector spaces. Modules. These are similar to vector spaces, but instead of having the scalars come from a field, it is only required that the scalars form a ring. If the ring is not commutative, then the module is defined as either a left or a right module depending on which side the scalars will be on. K-algebra. These are vector spaces with a field of scalars called K, where a bilinear product is also defined on the vectors. Group theory. Group theory is the branch of abstract algebra that studies the properties of the group algebraic structure. This includes understanding functions or maps from one group to another that preserves the group structure of both spaces. Such a map is called a group homomorphism. If the homomorphism is also one-to-one and onto, then it is called a group isomorphism and shows that the two groups have indistinguishable structure. Group theory includes studying groups in the abstract as well as applying those ideas to groups observed in the real world. Some important group theory ideas and results include normal subgroups, quotient groups, the classification of finite abelian groups, the Suloff theorems, Lagrange's theorem, and the three-group isomorphism theorems. Group theory has applications to quantum mechanics, crystallography, analyzing molecular vibrations in molecules, cryptography, error-correcting code, DNA structure and protein folding, and more. Ring theory. Ring theory is the branch of abstract algebra that studies the properties of the ring algebraic structure. Similar to groups, there are structure-preserving maps from one ring to another called ring homomorphisms. If they are one-to-one and onto, they are called ring isomorphisms and show that the two rings have indistinguishable structure. Ring theory includes studying rings in the abstract as well as applying those ideas to rings observed in the real world. Some important ring theory ideas and results include ideals, quotient rings, polynomial rings, principal ideal domains, the three ring isomorphism theorems, the division algorithm, and the Chinese remainder theorem. Ring theory has applications to solving Diophantine equations, cryptography, and algebraic geometry. Arguably, real and complex analysis are an extension of the study of the fields of real and complex numbers, respectively, and the study of functions on those sets. Field theory. Field theory is a sub-branch of ring theory that studies the properties of fields in abstract algebra. Because a field is a ring where the multiplication operation is commutative, has an identity element, and every non-zero element has an inverse, it is essentially a set where an addition, subtraction, multiplication, and division are all defined. This includes the well-known sets of the rational numbers, the real numbers, and complex numbers. However, it also includes the fields of rational functions, algebraic number fields, and finite fields such as the integers mod a prime number. Many fields can be realized as field extensions of another field. For example, the complex numbers are the real numbers extended by the number I. An important type of field extension of a field is called a splitting field of a polynomial with coefficients in the original field. This is the smallest field where the polynomial factors into linear factors. Such splitting fields are related to a corresponding Galois group, which we will reference again in a moment. Fields have many applications in mathematics and other fields of study. These include geometry, linear algebra, algebraic geometry, number theory, cryptography, error-correcting codes, and data transmission. Also, essentially all the sciences, including physics, chemistry, biology, earth science, computer science, etc., use either the real or complex number systems, and hence are applications of field structures. Galois theory. Named for and introduced by Évariste Galois, Galois theory builds a connection between group theory and field theory. The fundamental theorem of Galois theory relates certain field extensions to what's called its Galois group and builds a correspondence between the field extension's intermediate fields and subgroups of its Galois group. The topic of Galois theory was introduced to understand how to solve for the roots of polynomials. Galois was able to build a connection between polynomials that are solvable by radicals and whether its corresponding Galois group was a solvable group. This allowed for characterizations of many ancient problems, such as whether a compass and straightedge can be used to trisect an angle, or used to double a cube, or whether a general degree 5 polynomial can be solved by radicals. Galois theory produces proofs that each of these things are not possible. In fact, a general formula for solving a degree 5 or higher polynomial is not possible because many of the Galois groups corresponding to those polynomials are not solvable groups. While Galois theory itself may have limited applications to real-life problems, the development of Galois theory was an important motivator of group theory in general, and as such is connected ancestrally to all the myriad applications of group theory in the modern day. Linear algebra. Linear algebra is the study of the algebraic structure of vector spaces. Vector spaces are one of the most ubiquitous algebraic structures. Loosely speaking, a vector space is a space of objects that can have an n-dimensional grid placed on it and uses a collection of master directions called basis vectors to identify where vectors are located in the space. These spaces often have an inner product defined on them, which provides means to define lengths and angles and hence a geometry of the space. Linear algebra also discusses structure-preserving maps from one vector space to another. Such maps are called linear transformations. If they are also one-to-one and onto, they are called linear isomorphisms and show that the vector spaces have identical structure. Many important operations and functions are linear transformations, including reflections, rotations, scalings, shears, projections, the integral, the derivative, and other differential operators. Linear transformations between finite dimensional vector spaces can also always be represented by a matrix, and there are many results about matrices and transformations that are incredibly useful and important, such as determinants, eigenvalue-eigenvector problems, diagonalization, symmetric and Hermitian matrices, orthogonal and unitary matrices, canonical forms, and various matrix decompositions. Linear algebra has important applications to calculus, real analysis, differential geometry, ranking algorithms and search engines, linear programming, signal analysis, computer graphics, data science, machine learning, quantum computing, quantum mechanics, electromagnetism, electrical circuits, stress analysis, least squares approximation, genetics, graph theory, cryptography, Markov chains, economics, finance, Riemannian geometry, general general relativity, and many more. Numerical linear algebra. Numerical linear algebra is the intersection of numerical analysis and linear algebra. It includes the development, analysis, and application of practical and efficient algorithms for solving linear algebra problems. Two main focuses of such algorithms are efficiently solving systems of linear equations and efficiently computing eigenvalues and eigenvectors of linear transformations. Numerical linear algebra has the same applications as linear algebra, but is focused on numerical computations. These include applications to physics, mechanics, chemistry, finance, and more. Geometric group theory. Geometric group theory is the intersection of group theory, geometry, and topology. It studies the properties of groups by investigating the geometry and topology of the spaces that they act on and vice versa. It also includes the study of such groups themselves as geometric objects. This is done by applying a metric or length measure on the group. Representation theory. Representation theory is the study of abstract algebraic structures by representing their elements as linear transformations of vector spaces. This provides a simple perspective to study the properties of such algebraic structures and, in many cases, makes it easier to prove facts about those structures. Representation theory is applied in important mathematical ways to understand group actions, Lie theory, number theory, combinatorics, dynamical systems, knot theory, and the Fourier transform. There are applications of representation theory in mathematical physics, mechanics, string theory, engineering, control theory, robotics, coding theory, spectroscopy, crystallography, modeling DNA, signal processing, and more. Lie theory. Lie theory, named for Sophus Lie, is the study and application of objects called Lie groups and Lie algebras. These two classes of objects are related by a function called the exponential map, which creates a correspondence between Lie groups and Lie algebras. Lie groups are a geometric group that is also a differentiable manifold. As such, Lie theory is a branch of differential geometry. Lie algebras are examples of K-algebras where the field K is the real or complex numbers and the bilinear multiplication is the Lie bracket. The structure of the Lie algebra implies the structure of its corresponding Lie group. Aside from applications in solving differential equations, Lie theory has many applications in mathematical physics, where the Galilean, Lorentz, and Poincare groups are all examples of Lie groups. As such, Lie theory is particularly important in general relativity and astrophysics. Category theory. If abstract algebra takes concrete examples that share similar properties and abstractifies them into an algebraic structure, category theory considers the similarity in abstract mathematical structures and abstractifies that idea one layer further to study just that similarity in structure. This provides immense power to find facts that are true about all types of mathematical structures simultaneously. For example, why groups, rings, and vector spaces all have the same three isomorphism theorems is explained using category theory. Thus, category theory has applications in practically every branch of mathematics. However, category theory is also important in many areas of computer science research, such as functional programming and semantics.
Geometry and topology.
Euclidean geometry. Euclidean geometry most commonly refers to the geometry of the flat two-dimensional infinite plane. It is named for ancient Greek mathematician Euclid, who is well known for developing a system of 5 axioms that produces the geometry of this plane. Several other equivalent systems of axioms have been found. Higher dimensional Euclidean spaces have also been defined. David Hilbert proposed a set of 20 axioms for 3D Euclidean space, but for higher dimensions, the geometry is defined by the n-dimensional vector space Rn coupled with the standard dot product. Euclidean space is the basic form of geometry one typically learns in high school, and that single and multivariable calculus is based on. Until the discovery of general relativity, it was also thought to be the geometry of space, and Newtonian physics is based on this assumption. Trigonometry. Trigonometry, which literally means measuring triangles, is the study of the mathematics of angles and triangles and includes the study of the 6 trigonometric functions. Trigonometry is a subtopic of Euclidean geometry. The 6 trigonometric functions are periodic and have applications to more than just triangles. The trig functions also exhibit wave-like behavior and so have applications to any study of waves. Applications of trigonometry include surveying, aviation, navigation, astronomy, criminology, music, physics, and more. Analytic geometry. Analytic geometry is the study of the Euclidean geometry of the plane and 3D space using coordinates. This includes the treatment of the plane in either Cartesian or polar coordinates or other similar coordinate systems. Similarly, this includes the treatment of 3D space in Cartesian, cylindrical, or spherical coordinates or other similar coordinate systems. Analytic geometry is the point of view of Euclidean geometry that is used in calculus, physics, engineering, and other physical sciences. Applications of analytic geometry are primarily in physics and engineering, including aviation, rocketry, space science, and space flight. It is also part of the foundation of other mathematical fields of geometry, including algebraic and differential geometry. Hyperbolic geometry. After Euclid defined the Euclidean geometry of the plane using 5 axioms, it was thought for a long time that the first 4 of his axioms might imply the 5th. A lot of work went into trying to prove this, but to no avail. In the mid-19th century, mathematicians found an example of a space that satisfied the first 4 of Euclid's axioms, but failed the 5th. This proved that to obtain Euclidean geometry, one had to assume all 5 of Euclid's axioms, but it also showed that other types of planar geometries existed. This new type of non-Euclidean planar geometry was called hyperbolic geometry. Hyperbolic geometry most commonly refers to the geometry of the negatively curved two-dimensional hyperbolic plane. This plane is constructed using 4 of the 5 axioms that Euclid used to define Euclidean geometry. However, Euclid's 5th axiom concerning parallelism is replaced with the hyperbolic parallel postulate. This produces a completely consistent axiomatic system describing a non-Euclidean 2D plane. In this geometry, many facts that hold in Euclidean geometry fail. For example, the angle sum of a triangle is strictly less than 180 degrees, and given any line and a point off the line, there is more than one line through that point that is parallel to the line. For a more complete discussion of the discovery of hyperbolic geometry, I have a series of 2 videos that delve into this story. Links for those videos are in the description, and I hope you'll give them a watch. Higher dimensional hyperbolic geometries also exist and are typically defined in the language of Riemannian manifolds in differential geometry. Applications of hyperbolic geometry include crystallography, biology, cosmology, general relativity, and oddly enough, crochet. Hyperbolic geometry is also the inspiration for some of the imagery in H.P. Lovecraft's cosmic horror stories. Spherical geometry. Spherical geometry refers primarily to the geometry of the 2D sphere, such as the surface of the Earth or how we visualize the sky. Like hyperbolic geometry, this is another example of a two-dimensional non-Euclidean geometry, but in this case the space is compact. In spherical geometry, lines are great circles, and they behave very differently from Euclidean lines. Notable differences between spherical geometry and Euclidean geometry are that in spherical geometry, every triangle has more than 180 degrees, and there are no parallel lines. Applications of spherical geometry include navigation, GPS, astronomy, cosmology, and more. Differential geometry. Differential geometry is the study of the geometry of smooth spaces called differentiable manifolds. A manifold is a space that looks locally like n-dimensional Euclidean space. The manifolds are required to be smooth so that one can do calculus on them. Differential geometry extends the ideas first found in hyperbolic and spherical geometry to any kind of manifold. It combines ideas from calculus, topology, geometry, and linear algebra. The classical study of differential geometry began with understanding curves and surfaces in 3D Euclidean space, but was extended to abstract smooth manifolds not long after. Differential geometry is the language of general relativity, quantum field theory, and the standard model of physics. It finds applications in physics, chemistry, engineering, control theory, economics, computer graphics, machine learning, and more. Riemannian and semi-Riemannian geometry. Riemannian geometry is a subtopic of differential geometry that studies differentiable manifolds imbued with a metric that induces a smoothly varying positive definite inner product on the tangent vector space at any point on the manifold. This metric induces a geometry on the space, providing a length measure and definition of an angle measure. This also allows for the computation of the curvature of the manifold, as well as the straightest possible paths on the manifold called geodesics, which also happen to be length minimizing curves. If the metric is allowed to induce an inner product that is not necessarily positive definite, then the manifold is called a semi-Riemannian manifold. Space-time in general relativity is understood to be a curved, 4-dimensional, 3 space dimensions and 1 time dimension, semi-Riemannian manifold. In general relativity, gravity is realized as massive objects curving space-time around them, and objects traveling under the influence of the gravity of the massive object follow the geodesics of the space. Applications of Riemannian and semi-Riemannian geometry include general relativity, GPS, machine learning, robotics, computer graphics, information geometry, and more. Topology. Topology is the study of the properties of a shape that are invariant under continuous deformation. For example, how many holes a surface has is such a property called the genus of the surface. This is why a coffee mug and a donut are the same space topologically, since they each only have one hole and can be continuously deformed into each other. Topology studies these properties by considering an axiomatic structure on certain sets that are referred to as open sets. Topology is closely related to geometry, and indeed it has many applications to geometric fields of mathematics, such as differential geometry, Riemannian geometry, knot theory, complex analysis, and more. Topology also has many real-world applications, including topological insulators, topological data analysis, biology, chemistry, image analysis, and more. Algebraic topology. Algebraic topology uses concepts from abstract algebra to analyze topological spaces. These include important groups such as the fundamental group and other homotopy groups, homology and cohomology, manifolds, knots, simplicial complexes, and so on. Applications of algebraic topology include geometry, differential equations, neuroscience, physics, biology, engineering, data analysis, geographic information systems, neural networks, quantum mechanics, material science, and more. Differential topology. Differential topology is the study of the topological properties of differentiable manifolds, such as how many holes the manifold has, its homotopy type, and so on. This is in contrast to differential geometry, which is concerned with the geometric properties of such manifolds, such as distance and size. Differential topology has applications to general relativity to understand the topology of spacetime, quantum field theory, and more. Computational topology. Computational topology is the development, analysis, and application of efficient algorithms to solve topological problems. This has applications to computational geometry, graphics, robotics, social science, biology, chemistry, and more. Geometric analysis. Geometric analysis is the application of the study of differential equations to differential geometry and differential topology. This includes using geometrical methods to study and solve partial differential equations and using the theory of partial differential equations to solve problems in geometry. Moreover, it includes solving differential equations on manifolds as well as the calculus of variations. Important subtopics of geometric analysis include minimal surfaces and geometric flows. Geometric analysis has applications to general relativity, gauge theory, string theory, quantum mechanics, image processing, quantum computing, information geometry, mathematical biology, and more. Algebraic geometry. Algebraic geometry uses abstract algebra techniques to solve problems in geometry. The main object of study in algebraic geometry are the geometric versions of solutions of systems of polynomial equations. Such solution sets may be curves or surfaces. Solution sets that are curves are the most commonly studied. Questions about such curves range from their singular points to the topology of the solution set. Applications of algebraic geometry include coding theory, cryptography, robotics, computer vision calibration, computer-aided design or CAD, 3D printing, string theory, quantum field theory, and more. Knot theory. Knot theory is the study of mathematical knots. Though inspired by physical knots, a mathematical knot differs from physical ones in that both ends are joined together. Mathematically, a knot is the image of a circle under a one-to-one continuous map into R3. Two knots are considered equivalent if there is a way to continuously deform one knot into the other without breaking it. An important problem in knot theory is knowing when two knots are equivalent. One way to do this is to compute various knot invariants, which are quantities that don't change under a continuous deformation. If two knots had different values of an invariant, then they are definitely not equivalent knots. There are applications of knot theory to biology and DNA analysis, chemistry, quantum physics, robotics and cable control, computer graphics, cryptography, manufacturing, and more.
Discrete mathematics.
Discrete mathematics. Discrete mathematics is the study of mathematical structures that are considered discrete, as opposed to continuous ones that are found in the real numbers, calculus, or most types of geometry. This includes the integers, graphs, sets, and logic. Discrete objects can usually be enumerated with the integers and so deals most often with countable sets, but this isn't all-inclusive of discrete mathematics. Discrete mathematics has applications to computers, networks, web searches, navigation, scheduling problems, cryptography, apportionment of democratic representatives, computer graphics, voting, data science, logistics, and more. Logic. Mathematical logic is the study of formal logic in mathematics. This includes understanding models, proofs, sets, and recursion. Important ideas in logic include statements, which are sentences that have a defined truth value of true or false, conjunctions like and or to connect statements, the universal and existential quantifiers, propositional functions, conditional statements, negations, converses, contrapositives, and so on. Logical fallacies are arguments that violate the behavior of one or more of these logical connectives. What I have described here are parts of what is called propositional and first-order logic. However, other systems of logic exist and are studied by mathematicians and philosophers. These include second-order logic, infinitary logic, and non-classical logics. Logic is the foundation of all mathematics, but also has applications to philosophy, computer science, linguistics, social science, and more. Boolean algebra. Boolean algebra, named after George Boole, is the algebra of logical expressions. Boolean variables take values as true and false, usually denoted by 1 and 0 respectively. The operators on Boolean variables are logical operators like and, or, and negation. Boolean algebra provides a formal way of expressing logical operations. Boolean algebra has natural applications to computer science, electronics, machine, and programming languages, but because of its ability to express logic, also has applications to basically all of mathematics and philosophy as well. Set theory. Set theory is a subtopic of mathematical logic that studies sets. Like algebraic structures, to prove things about sets, the sets are required to satisfy certain axioms. The most common axioms assumed for sets are the axioms set out by Ernst Zermelo and Abraham Fraenkel, called Zermelo-Fraenkel set theory, with the axiom of choice, or ZFC set theory. The ZFC set theory forms the foundation of most other topics in mathematics. Important ideas in set theory include the intersection and union of sets, cardinality, infinity, Venn diagrams, functions between sets, the axiom of choice, and the continuum hypothesis. Many mathematicians specializing in set theory are also interested in the implications of the ZFC axioms and other set theories where those axioms are not necessarily assumed. This study has led to a deeper understanding of the implications of the Zermelo-Fraenkel axioms. For example, Paul Cohen in 1963 used a set theory technique called forcing to prove that the axiom of choice and the continuum hypothesis were independent of the Zermelo-Fraenkel axioms, meaning that there are models of Zermelo-Fraenkel set theory that satisfy the axiom of choice and/or the continuum hypothesis, and those that don't. Applications of set theory, besides pretty much all of math, include computer science, logic and philosophy, probability and statistics, information theory, linguistics, and more. Combinatorics. Combinatorics is primarily about counting, particularly how to count complicated combinations of things. Historically important ideas in the subject of combinatorics include the Fibonacci numbers, counting permutations, combinations, and partitions, the binomial coefficient, Pascal's triangle, the bridge of Königsberg problem, and so on. More modern considerations in combinatorics include partially ordered sets, lattice theory, and more. A far more complicated branch of mathematics than it sounds, combinatorics has important applications to probability, graph theory, communication networks, cryptography, computational molecular biology, computer architecture, languages, pattern analysis, databases, and many more. Graph theory. Graph theory is the study of objects called graphs that model pairwise relations between objects. Each object is represented as a node, and each relationship is represented by an edge connecting two nodes. Edges can be directed or undirected. Graph theory is the study and analysis of such graphs and their properties. Applications of graph theory include gerrymandering and voting, networks, database management, algorithm design, biological networks, phylogenetics, social network analysis, opinion dynamics, transportation, logistics, chemistry, finance, computer science, and more. Network theory. Network theory is a branch of graph theory where each edge in a graph carries attributes such as a magnitude or to indicate something concrete such as influence, communication, or location. Essentially, network theory is the application of graph theory to real-world problems. One of the main ideas of network theory is the idea of network centrality, which are various measures of which node in a graph is central in some sense. For example, a network of web pages where the web pages are nodes and the edges are links between web pages can be ranked according to a centrality measure known as PageRank, which was developed by Google and is one of the primary ways that search engines will list results. Applications of network theory include electrical grid analysis, social network analysis, biological network analysis, and more. Number theory. Number theory is the study of mainly the integers and arithmetic functions. Some of the primary objects studied by number theorists include the prime numbers and mathematical objects that can be constructed from the integers, such as the rational numbers or the algebraic integers. While concerning primarily the integers, many analytic techniques and ideas are used to understand concepts in number theory, such as the Riemann zeta function. Number theory that employs ideas from analysis is referred to as analytic number theory. On the other hand, rings of algebraic integers can be viewed as lattices in Rn. The geometry of such a lattice informs our understanding of the corresponding ring. Number theory that employs ideas from geometry is referred to as geometric number theory. The importance of number theory was touted by Carl Friedrich Gauss when he said that mathematics is the queen of the sciences and number theory is the queen of mathematics. Whether or not all mathematicians feel the same way, number theory certainly has incredibly important applications to cryptography, data security, computer science, coding theory, financial mathematics, and more. Discrete geometry. Discrete geometry is the study of combinatorial properties of geometric objects. This mainly includes answering questions about finite sets of basic geometric objects, such as points, lines, or polygons. This includes tessellations of the plane, polyhedra, circle packings, map colorings, finite incidence geometry, and more. Discrete geometry has applications to other parts of mathematics, such as graph theory, topology, and algebra. It also has real-world applications to computer graphics, robotics, image processing, network design, crystallography, and more. Discrete optimization. Discrete optimization is concerned with optimizing functions where the variables are discrete and not continuous, such as the integers. This applies to optimizing problems in graphs, matroids, and over the integers. Discrete optimization finds applications to bioinformatics, telecommunication network design, circuit design, resource allocation, finance, logistics, and even sports scheduling. Information theory. Information theory concerns the quantification, storage, and communication of information and uses mathematics to understand these ideas. This applies to how information is stored and processed not only in computers, but also in other kinds of physical and biological objects such as brains. Applications of information theory include data compression, error detection, statistical inference, cryptography, neurobiology, signal processing, bioinformatics, quantum computing, information retrieval, pattern recognition, music, philosophy, and much more. Game theory. Game theory is the mathematics of decision-making in strategic settings. Such settings are referred to as mathematical games since games are a type of such a setting. However, many economic, political, and social situations are also a strategic setting that game theory can help us understand. The study of game theory concerns modeling strategic settings to understand the kinds of strategic behaviors that a game would incentivize and how players may optimize their behavior within such settings. Game theory has applications to economics, actuarial science, voting, politics, international affairs, computer science, and more.
Statistics.
Probability. Probability is the study of the likelihood of events measured as a value between 0 to 1, indicating what fraction of the time that event occurs. This includes both where the outcomes are discrete and where they are continuous. Discrete probabilities can typically be handled with arithmetic, but continuous probabilities require the use of calculus and eventually measure theory to compute them. Important ideas in probability include random variables, probability distribution functions, cumulative distribution functions, expected values, variance, and more. Probability plays a key role in statistics. Probability has applications to statistics, physical life and social sciences, finance, gambling, artificial intelligence, machine learning, computer science, game theory, and more. Statistics. Statistics is the development and study of methods for collecting and analyzing real-world data in order to make conclusions about larger groups of populations. Two main ideas that statistics is concerned with is uncertainty and variability in observed data. Because of this, statistics heavily involves applications of probability. Moreover, as practically all of science uses empirical data to study reality, statistics has a myriad of applications. For example, statistics finds applications to physics, biology, chemistry, economics, environmental science, forensics, epidemiology, demography, geography, law, actuarial science, machine learning, data science, ecology, psychology, social science, political science, finance, sports, and so much more. Descriptive statistics. Descriptive statistics are measured quantities from a collection of information that summarizes some feature about that information. The topic of descriptive statistics is the study and analysis of such measured quantities. Examples of descriptive statistics are measures of central tendency, like the mean, median, and mode, and measures of variability, such as standard deviation, variance, max and min values, and so on. Descriptive statistics are used to describe features of a particular set of data. These have applications practically anywhere data is used, including in all the physical life and social sciences, healthcare, economics, business, government, sports, and more. Inferential statistics. Inferential statistics is the process of using data analysis about a sample to infer properties of the population from which the sample originates. Most often this means drawing conclusions about the descriptive statistics of the whole population based on the descriptive statistics of the sample, but may also include making predictions about the whole population. This inference often relies on an assumed model for the population and how the sample would have arisen from that model, followed by testing hypotheses and deriving estimates given that model. The main difference between descriptive statistics and inferential statistics is that descriptive statistics are exact measures about the sample of data we have, while inferential statistics try to infer information about the wider population from information about the sample of that population. Applications of inferential statistics include anywhere data is available about samples, but information about the entire population from which the sample came is desired. Usually that population is so large that it would be impractical to obtain that information directly. This includes applications to the physical life and social sciences, market research, clinical trials, political polling, economic forecasting, and much more. Data science. Data science is the application of statistics, linear algebra, scientific computing, visualization, and algorithms to model and analyze data structures, obtaining insights about the data and the real-life phenomenon the data represent. Data scientists include developers that design and analyze algorithms to extract and extrapolate information from data, and users that utilize those algorithms to do actual data analysis and create insights from real-life data. Much of data science tends to focus on prediction rather than inference. Applications of data science include healthcare, disease identification and prediction, transportation, sports, government, e-commerce, gaming, social media, fintech, and so much more. Data science is currently one of the fastest growing and most in-demand subjects of mathematics and industry. Actuarial science. Actuarial science is the application of probability, statistics, game theory, and economics to solve the specific problem of assessing risk in insurance, pension, finance, and investments. Actuaries are employed primarily by insurance companies to compute the premiums that they charge that will both cover the costs for their clients and turn a profit for the company. Actuaries are employed in other industries to perform similar tasks. Actuarial science has applications to insurance, healthcare, finance, and economics. Non-parametric statistics. Non-parametric statistics refers to statistical analysis that makes minimal assumptions about the probability distribution of the underlying population from which a sample originates. This includes methods that are distribution-free and do not depend on a parameter like the mean or a variance. But it also typically includes techniques such as non-parametric regression that assume that the structure of the model may vary. Non-parametric models use the data to determine the structure of the model rather than assuming the data conforms to some model in advance. Because non-parametric statistics make minimal assumptions, they have a wide variety of applications, including analyzing rank data, preference studies, and when the underlying distribution of a population is unknown. This includes applications to financial analysis, psychology, education, healthcare, market research, social science, and more. Mathematical statistics. Mathematical statistics is specifically the application of mathematics to statistics instead of a focus on collecting statistics data. This includes applications of various branches of mathematics, including probability, real analysis, linear algebra, stochastic analysis, differential equations, and measure theory. This plays a major role in statistical inference. Much of mathematics Mathematical statistics deals with developing and improving statistical procedures that can be used in statistical research. Topological data analysis. Topological data analysis is a type of data analysis that uses the shape of a data set to understand information about it. Ideas from topologies such as metrics, algebraic topology, and homology are applied to data sets to understand the shape of that data. The main tool of topological data analysis is called persistent homology. This idea takes a data set and by applying a metric can reduce the data set into a simplicial complex. The topology of that simplicial complex can then be used to better understand the behavior of the data. Topological data analysis has applications to medicine, material science, image analysis, biology, data science, geography, electoral redistricting and gerrymandering, and more. Biostatistics. Biostatistics is a branch of statistics focused on the analysis of living things with a heavy focus on people. Thus, biostatistics often is interested in data that may change over time. The most common methods in biostatistics are survival and longitudinal analyses. Biostatistics is most commonly used in pharmaceutical companies to help develop treatments for various ailments. Methods from biostatistics are also used in genetic research and thus are applied to additional fields such as biology. Stochastic analysis. Stochastic analysis is the study of stochastic processes. Stochastic processes are random processes defined on a family of random variables that change with time. Such random processes are used in many mathematical models of phenomena that appear to vary randomly. Stochastic analysis uses mathematical techniques from probability, calculus, linear algebra, set theory, topology, real analysis, measure theory, and functional analysis. Stochastic analysis has applications to biology, chemistry, ecology, neuroscience, physics, image processing, signal processing, control theory, information theory, computer science, finance, economics, and more. Ergodic theory. Ergodic theory studies statistical properties of deterministic dynamical systems. This uses mathematical techniques from measure theory and probability to understand the statistical behavior of deterministic dynamical systems, particularly when such a system is run for a long time. The main idea of ergodic theory is ergodicity, which is the quality that some dynamical systems possess that a point flowing in the system will eventually move through every point of the space that system moves in. Ergodic theory has applications to statistical physics, signal processing, financial mathematics, number theory, differential geometry, probability theory, and more.
And that's it for every type of mathematics there is. Did we miss your favorite type of mathematics? If so, let me know in the comments. This video is a compilation of 5 every type of math videos covering the 5 major branches of mathematics. You can find those individual videos in a playlist here. If you enjoyed this video, please give it a like and hit that hype button. And subscribe to Scholar Sauce to catch all the amazing content from our channel, including videos like this one where we find that classic JRPG world maps aren't actually spheres. And we'll see you next time on Scholar Sauce.